Hello all, welcome to the course AI driven perception learning and mapping for drones. In this particular session, we will have a basic tutorial for maths for AI. So the learning objectives are essentially to understand why is maths foundational for AI, and we'll also go over basic math operation and basic calculus in this particular tutorial, moving on to some advanced concepts in the next tutorials. Now, why is mathematics important for data science and AI? It is because it is the foundation of algorithmic designs. So many AI algorithms depend upon basic or foundational concepts like calculus, linear algebra and probability. These are also some of the prerequisites for this course, and we do expect a basic understanding of linear algebra and calculus and probability. Mathematics is also important because for representing data and knowledge that is retained in specific data sets, we actually represent these values with vectors, matrices and tensors. Now in fields like computer vision and natural language processing, these matrices have a very fundamental importance in the input data itself. For example, if we have an image or an RGB image, we actually have three matrices with channel as 3 used to define the input data, right? So again, input, even the parts of the neural network, the whole pipeline does require an interpretation in terms of matrices, vectors and tensors. Lastly, we want to develop algorithms which learn from data, right? And hence these are we use statistical methods to make predictions and decisions throughout the whole process. We also use certain patterns and certain metrics to measure the uncertainty and how well the algorithm is performing. For this also, we need to have a quantifiable number to measure what is the uncertainty of any particular algorithm. Now coming back to some other reasons, we also use optimization techniques while training our learning algorithm. This is something we will keep reiterating again and again while training either a single layer perceptron or multi-layer perceptron or even deep models. Since we use optimization techniques, it is very important to understand how do we formulate these optimization. Mathematical functions and models are also used to evaluate the performance of various AI algorithms. These metrics are accuracy, precision, recall and area under the ROC curve. We also use mathematical logic to enable reason, problem solving and decision making. Right. Now specifically talking about neural networks and deep learning, we use a very foundational algorithm known as backpropagation algorithm, which is used to train neural networks. This is essentially trying to compute the derivative or the partial derivative with respect to weights and then trying to update the network parameters. For this also, since using chain rule and partial derivatives, it is important to have our basics clear. Lastly, if we talk about certain fields, for example, if we talk about computer vision, we do require concepts of linear algebra and calculus, which is to understand the image data. And when we go into different modalities, like let's say from an RGB image to a IR image or a SAR image, we do want to see how is the data represented in a very fundamental matrix form. For uncertainty and inference, we require topics like probability and Bayesian statistics. This is essentially to understand how the model is reasoning and how to measure the uncertainty in any model. Whenever we are deploying a model, we want the model to be very accurate. However, we know that the real world scenarios are ever changing, and since change is the only constant, we want to be very clear where the model is failing, which is why we want to always quantify the uncertainty in these scenarios. Lastly, if we talk about scalability and big data, we want to essentially form large and diverse data sets. And these large and diverse data sets is not only a qualitative sense, we also want to quantify what does it mean when I say it's a large and diverse data set. What do we mean by diversity in data, right? So these are some things we want to quantify with in a mathematical sense, which is why we would also have a series which is Math for AI, where we will try to understand some basic concepts, and using MATLAB we will try to plot and see the influence of various factors during the learning algorithm. Although we use MATLAB because it is convenient for us, you are encouraged to please use MATLAB or even Python, whichever you are more comfortable with. Essentially in the MATLAB sessions also, we may not focus mostly on the syntax part of it. We assume that those syntax could be resolved. We want to focus on the deeper understanding of what is the math operation that we are focusing on, and how does it help, or what intuition can we develop when we are observing it in the learning algorithm. So in the next part we will start with the MATLAB session. However, again the focus is not on the syntax, the focus is on the understanding of basic math functions, right. So specific to this tutorial, we will quickly go over vectors and matrices, some of the symbolic math, and calculus, which is derivation and integration. Okay, so let's go over the first part of the tutorial. We'll go over certain fundamental operations in MATLAB, and we'll start with the basic operation in mathematics, which is essentially some basic operators, linear algebra and plotting. We'll also quickly give an overview of the calculus of it, so essentially the differentiation and the integration, and then understand what does it mean to attain an extreme position in calculus. So essentially we'll try to understand from plotting the graphs the interpretation of derivatives and what does it mean when we say a minima or a maxima. Okay, so in this MATLAB we'll basically just try to run this MLX file. Once we run it, we'll try to go over certain operations, or else let's start. So in this particular tutorial, let's go over basic operations like basic operations, and then on understanding of vectors, matrices, and also go over loops, which is for loop and while loop. Now why is for loop and while loop really important for us? It's because whenever you have a learning algorithm, the learning algorithm actually operates in a loop, right, and we have certain criterias for stopping and certain criterias for convergence, where after it has attained that condition, we go out of the loop and say that okay, the training process is completed. Even in the lectures, in the subsequent lectures, you will see us using directly an algorithm in the form of a loop, where we will say while this condition is satisfied, keep iterating the loop, and once we have attained convergence, we will drop out of the loop. So loops are essentially how we train train any learning algorithm and other deep learning models, and we'll keep using these loops throughout our whole lecture series. And then we'll quickly go over the matrix operations, lastly concluding this particular session, this particular topic by its plot on a 3D surface. Okay, so let's go over the basic operations which is specific to MATLAB. Let's go over by defining certain variables. So if we write b is equals to 4, it is essentially defining that that variable. If we write c is b plus a, it is essentially initializing c with the value of a plus b. In this condition, b is 4 and a is 2. If we define d as b a minus b, we observe the value of d as minus 2. If we write the variable e as a into b, it is essentially trying to multiply a and b, giving us a value of 8. If we define f as the division operation of a divided by b, we get the value of f as 0.5. If we define a variable g as an exponential of a, it is essentially writing it at exponential at the rate of a, which is giving us a value of 7.38. If we write h as a sinusoid of a, which is h is equals to sine of a, we get a value of 0.90. And lastly, we can define the same thing for a cosine function, and we get the value of I as cos of b. Okay, now let's look at vectors. So essentially vectors are very important for us. In single layer perceptron, you would essentially start using vectors, and then as we go on deeper models, you will see the importance of vectors and matrices. So if I want to create a vector, vec, which is VEC is given as vector of 1, 2, 3, 4, 5. Now essentially we can also see that it has certain rows and columns, right, and this is a proper interpretation in MATLAB. So if I say 1, it is essentially 1, 2, 3, 4, 5 and specific to each column. If we use the syntax size of vec, it is essentially telling us the number of rows and columns. In this particular example, it is 1 row and 2 columns. Okay. Let's say that we use this particular syntax, which is vec underscore 100 is from 1 to 100. It is essentially going to create a vector which has 100 numbers with the step size of 1. So it's going to go from 1, 2, 3, 4 right up till 100. So as we can see here, we'll see right up till 100, right. So this is a vector. If we want to print the size of vec underscore 100, it is essentially given as 1 and 100. So 1 row and 100 columns. If we perform an operation of transpose, it is essentially a interchange of the size of rows and columns. So vec underscore 100 was 1 cross 10 as we observe here. However, vec and the transpose vector vec underscore t is essentially 100 cross 1. Okay, and similarly if we also print the size of vec, it is given as 100 and 1. So essentially 100 rows and 1 column, so it's interchanged. Lastly, we can use something like indexing. So we have a vector that we have defined, and from the whole vector we only want to identify certain indexes, right. So if I say vec underscore t of 1, the answer is 1. Why? Because if I look at this particular vector, I can see that at an index of 1 the value is 1, right. Similarly, if I say vec underscore t of 50, it's going to give me a value of 50. Why? Because if I again look at vec underscore t, we can observe that this value does give us 50, right. And lastly, vec underscore t of end, which is the last index. In Python we also use -1. That's essentially giving you the last element of that particular vector. For us it is 100 in this case. Now let's go over matrices. So matrices is somehow similar to vectors, but let's again take a quick look. So when we define mat as 1, 2, 3 semicolon 4, 5, 6 semicolon 7, 8, 9, it is essentially highlighted by this equation, this particular notation. So we can see that it's a matrix which is 3 cross 3, and we can identify all the elements here, right. Now again, this is a square matrix because the row and columns, the number of rows and columns are same. If we write as size of med, it is essentially giving us the number of rows and some number of columns. It is also giving, okay, so it's 3 and 3 in this case, 3 rows, 3 columns. If we take a transpose of mat, it is essentially just to performing a transpose. So we had 1, 4, 7 here in mat. The transpose of mat would give you 1, 2, 3 and so on for the other rows and columns. Now let's define a rectangular matrix which is given as rect underscore mat, which is essentially 1, 2, 3 semicolon 4, 5, 6, which is highlighted here. If we see the size of rect underscore mat, it is essentially 2 rows and 3 columns, which is what it prints here, which is 2 rows and 3 columns, right. Okay. If we take the transpose of rect underscore mat, essentially getting rect underscore mat underscore t, this is again taking the transpose of the rectangular matrix that we defined earlier. So we saw the rect with 2 rows and 3 columns. For the transpose, it is the other way around. Okay. Now once we have defined matrices or even vectors, we can actually access particular elements in that matrix. So for example, rect underscore mat underscore t for 1 to 1 is essentially the 1 to 1 element, which is 1 in this case. Let's take rect underscore mat underscore t 1, 2, that is essentially 1, 2, which is giving us the fourth which is giving us 4. If we take rec underscore mat underscore t of 2 comma 1, it is essentially giving us 2. So we can just use the indexes here and then find out the element. Okay. Now let's also quickly overview the loops. Now one example that we can use for the loops is, how do you compute the loop of factorial 5? It is essentially computing the multiplication of 5 into 4 into 3 into 2 into 1, and this could be written as a loop, and we could follow the same operation for, let's say, 10 factorial, 50 factorial and 100 factorial. So let's say we define n as 10, let us define f as 1, and we will use this particular loop. So for I is equals to 1 to n, which is essentially looping from 1 to 10, we will perform the factorial operation, which is f is f into I, right? And at each operation during the loop, it would print these values. So for iteration 1, the value of f is 1. For iteration 2, the value of f is 2. The iteration at 3, the f value is 3. So essentially the factorial of 3 is 6. Iteration 4, the value of f is 24, because the factorial of 4 is 24, and so on. It can go on for a very high number here. Okay. Now let's also take a look at while loops. So in for loop, we actually specify the value of I from what part it should start and from what part it should stop, right? So from I from 1 to n, it should stop when it's about to reach n. Now for while loop, we actually don't have that constraint. What we do is essentially while n is greater than 1, which is the loop will always operate while n is greater than 1. We can reduce the value of n is equals to n minus 1, which is reduce the value of n at every iteration or step, and then compute the factorial. Now if we keep doing that at each of the loops, as observed, n starts at, let's say, 9, we will get the value of f and so on. And for each iteration, the value of n keeps decreasing. When it reaches the value of n is 1, this constraint that n greater than 1 is violated, which is why it comes out of the loop. Okay. Now let us look at something different here, which is, let us create a vector or a matrix with some random integers, and this is something which is useful for us because when we go to different learning algorithms, we see that we need to initialize the weights randomly and then perform a learning operation. So in case we are doing that, let's define a as rand I 100 comma 10 comma 1. Essentially what it is doing is, it is coming up with a matrix of dimension 10 cross 4, and it is initializing each element in 10 cross 1 size from 1 to 100. So essentially in the first part, it will identify all the values from 0 to 100. It would just initialize randomly any values from 1 to 100 and so on, right? Now let's assume that, okay, so once we perform this operation, we actually have defined A, and we can also identify that for each particular indexes what are the elements, right? Now if we give a constraint of A less than 50, this is essentially identifying all the elements where the value is less than 50. If that is done, then we get a list of indices. Now this list of indices is similar to the shape of A. However, for all values where A is less than 50, it gives us 1, and for all value where this constraint is violated, it gives us a value of 0. So if I look at this particular value of A, so I get 17 for the 2 comma 1 position, and similarly I get a value of 1, which is essentially, it's generating a mask. The mask is giving you a value of 1 where the constraint is true. The mask is giving a value of 0 where the constraint is violated, right? We can do something similar here, which is, once I have this mask, and this is actually an important operation that people do generally use when they are using or training certain models, because you generally want to identify certain parts of the model. So where is the highest activation, where is the lowest activation, right? So I have a feature map, I want to identify in which parts of the feature maps the activation is the lowest, which is why we have a constraint. So once we use the constraint, I know the location of all the elements where this constraint is true. Now although I have the indices, let's also try to get the values where this is true. So if I pass this index, which is essentially we call it as a mask. Mask is, it's a mask of ones and zeros. If I pass it through A, which is essentially the matrix that we defined, which was randomly initialized, we get this particular tensor. So it's giving me all the indices with all the values, right? And it will go on until we get all the values where A is less than 50. Okay. Now let's also take a look at an example where we have the elements as either 1 or 0. So let's assume we define mat1, which is ones of 4 and 6. We would essentially get a matrix of dimension 4 cross 6 and all the elements here are ones. If we do the same, which is mat of 0 is zeros of 5 comma 3, we get a matrix of 5 cross 3 and all the elements here are 0. Lastly, if we define I is equals to I of 5, I is essentially, so EYE essentially is used to define an identity matrix. Identity matrix is you have 1 across all the diagonals, everywhere else it is 0. So I is 1 across all the diagonals, everywhere else it is 0, right? Okay. Lastly, let's do some basic math operations on these matrices that we have initialized. So let's say that we have A, which is rand I of phi 2 comma 3. It's essentially generating it's generating a matrix of 2 cross 3, and I initializing it with the values with 5 as its constraint. So from 1 to 5 any values could be taken and it could be updated. Each of the element it could be initialized. Now similarly we do the same operation for B and we write C as A plus B. If we write C as A plus B, it is essentially doing an element wise addition for each element in A with each element in B, and again this is only possible if the dimensions of A and B are same. In case they are not same, this addition is not possible. Similarly we can also do a subtraction. So D is defined as B minus A, where we perform an element wise subtraction. Okay. Now let's look at this operation, which is B square, which is given as B dot at the rate 2. So it is, what it is trying to do is it is doing an element wise square. It's not really matrix into matrix, right? It is not B transpose B. It is element square of all elements in B. If I have B times B, this is essentially multiplying the B matrix which itself. So it will be B transpose B. And lastly we can come up with a certain different kind of an operation. So E is A transpose times B. So essentially I had a matrix A, I had to take its transpose and then we multiplied by B. Okay. Lastly we also have certain operations. So F is given as E by 100. So we will divide all of these numbers by 100 F is defined as E by 10. So all of these elements in E will be divided by 10. So it's an element wise operation. Okay. Lastly we also have an inverse of F. So an inverse of F is represented as G and we can compute its value. So the value of G is highlighted here, right? And similarly we can also do it for H, which is the inverse of B transpose A times B divided by 10. So essentially a very complicated math operation could also be done and we can get H directly, right? Now let's go to the other part, which is the plotting of different functions. And this is actually important for us because it gives us an idea of how the plotting or how the learning algorithm should be made. And okay, let's come to that. So let's use MATLAB to visualize some basic math functions in 2D and then in 3D. So y is given as a1 sine omega 1 x. So here y and x is the input, y is the output. A1 is the amplitude which we define as 1, omega is the frequency which we define as 1. X is given from 0 to 10 with a step size of 0.1. So for each step size of 0.1 we would have certain values of y and that we would try to plot, right? Again just to reiterate, we are not very keen on the syntax part of it, although yes, if you are using MATLAB or if you plan to use MATLAB, the syntax is important. If you are using Python also, the same syntax for Python is important. However, the focus in the tutorial is just to understand the interpretation of what the code is doing and what the plot would highlight, and we'll go to the plot in a couple of minutes. So let's say we have the value of y Now if we look at the value of y, it is essentially 1 cross 101, so it's actually a vector, right? And at each step size, which is y, at each step size we have its corresponding value, and the value is identified from here, right? So depending upon the step size, the size of the vector would change. Now let's just quickly plot x and sine 1. There's sine 1 because omega 1 was 1, right? So let's plot y is equals to a1 sine omega 1x, which is given by this equation, right? And let's also simultaneously plot another sine curve, which is a2 is 1.5 and omega 2 is 3. Now if we do that, we can see the curve on the right, right? This is a very basic sine curve. We plot two sinusoids, one with a magnitude of 1, the other with a magnitude of 1.5. So we can see the amplitude is, so a1 is 1, a2 is 1.5, and they operate with different frequencies, right? Now let's take a look at the summation of this. So let's define z is equals to a1 sine omega 1x plus a2 sine omega 2x. If we do that, then the plot is actually observed on the right. So we have sine 1, which is a different curve which we can identify here, and we have various values, and similarly we have the value of sine wave 2 as well, and when we add both of them, which is essentially what z means, this equation, we get the value of z, which is highlighted by the second equation. Okay. Now let's go to an interesting plotting on the 3D space. Let's define z is sine omega 1x plus cos omega 2y. Essentially if I look at this equation, I have two variables, x and y, right? And z is essentially the third variable which depends on x and y. So it is a function of x and y. Now these are essentially a function of independent variables, and let's see what happens when we plot it in the 3D space. Now again, whenever we are plotting, we have x and y and we have their corresponding timestamps, right? Step size, right? So it starts from -1 and it goes till 10, and it goes to 10 with a step size of 0.1. The same goes for y, right? And essentially we have the value of z here, which is sine x plus cos y. Okay. Now let's look at the plot here. The plot essentially looks like this. So the axis is y axis here, x axis here, and the z axis which represents as the amplitude. Now we observe, and this is something which is very important because we will see a graph very similar to this for a single layer neuron training. So we have a loss, this represents very similar to how a loss function would look for us in that case. So if we initialize the weights here, our goal would be to minimize the loss as we keep identifying, but okay, we will come back to that. This is how the graph looks, right? Now let's do a contour plot of it. Contour plot of it is essentially we are looking at the 3D graph, and from the 3D graph we are looking at the xy plane. Now if I look at the xy plane, we observe that there are some values where the amplitude is -1.5, so it's very low, which is identified by this contour here, and we also see some yellow contours which is essentially 1.5, right? Okay. Now if I look back at this curve, I can observe that the top portion of this curve is yellow in nature, and the bottom portion, which is the minimum value, identifies as a blue shade. Okay. Lastly, let's also look at an example where we are trying to plot the similar curve, but we are essentially trying to plot the similar curve but with different omega. So the frequency for one sinusoid is 1.5 and the other is 2. If we do that, the curve looks a little bit more edgy, right? Because your frequency is more, so the number of sinusoids in one particular bandwidth is increased. So now when you look at this compared to the earlier ones, it is a little bit edgy. It has more minimas, I would say, compared to what we had seen earlier. Okay. Now let's quickly go over our definition of derivatives, right? So in MATLAB you have something known as symbolic math. Now in symbolic math, let's go around defining these symbolic variables and let's see if they can be used to simplify the equations which we make using them. So SYMS ABC is essentially defining these symbolic variables. Once we define it, C is given as a square plus b square, which is clearly observed here. Now if I use SUBS, which is subs of C, A comma B and then 4 comma 4, this is essentially just substituting the value of AB as 4 comma 4 and giving us the value of C. So the value of C in that case would be 32. Okay. Let's also use a command of simplify. So let's define SYMS, which is the symbolic variable of x. Let's use the simplify equation, which is x square, and okay, the argument is x square minus 5x plus 4 divided by x square minus 4x plus 3. Essentially these are two quadratic equations. What the simplify would do is essentially cancel out whatever are the common factors and it would give us an answer. In this case it is x minus 4 divided by x minus 3. Let's also try to use a solver here. So let's use the solve command. So let's again define the variable as SYMS x. Let's solve this as x square plus x cube plus x square minus 2 is equals to 0. The solve equation is for the variable x itself, right. Now the answer to this is 1 minus 1 minus I minus 1 plus I, because essentially we have complex valued roots. Now in the same example, if we only want to assume the value of x as real, then the answer would only be 1. The complex valued elements would be removed, right. Now let's also try to use the double command, which is essentially just trying to solve this equation but trying to change the floating values. So x underscore sim is given as solve of x square minus 1 is equals to 0. Solve this equation for the variable x. We get x underscore sum as minus 1 1. If we use the double, it is essentially changing the floating points. Since this is an integer, it's not effective, but in case it was a floating point number, the decimals would be adjusted. The digits after the decimals would be updated. Let's quickly go over differentiation in MATLAB. So the differentiation function is defined in this manner, which we have always seen. F dash x is given as derivation of fx with respect to x, which is given as limit of h tending to 0 fx plus h minus f of x divided by h. If we use the function differentiation diff in MATLAB, it actually does the differentiation. So first we'll clear all to remove all the initialized variables. We will use SMYSX, which is defining the variable. Now f of x is defined as 3x square, right, which is given as this value. Now if we do f of 1, it gives us the value of f of x at x is equals to 1, which is 3. F of pi is 3 pi square. F of 1 is a composite function, so it is f of 1 was 3, so f of 3 is 27. Now if you want to plot this particular graph, this is how it looks. So this is how it looks. This is the graph that can be seen. We can see that, okay, so this is the plot of f of x versus x, right. So f of x is on the y axis, x is on the x axis, right. Now once we have this, let's try to take the derivative of f of x with respect to x and define it as gx. So gx is given as the differentiation of f of x at x, right. If we do that, the plot of g of x versus x is essentially a line, right. Okay, now let's look at the geometric interpretation of a derivative. For any function f of x, the derivative at the point x0 refers to the slope of the tangent at that particular point. So if we have this parabola as we observe here, which is in the red curve, if we take the derivative, which is represented by this line, this is essentially the direction of the tangent. Okay, so let's use the same logic here. Let's define SYMS y and x. the value of x1 is 3, the value of y1 depends upon f of x1, we have m which is the slope, we have y is mx minus x1 plus y, which is a very standard linear the equation of a line. Now this is how the derivative would look like. So we have in the blue we have the curve which is f of x, and we have the red color line which is g of x. Now let us see the value of x as x is equals to 5. If we take the value of x is equals to 5, we observe that the equation of the line changes because the value of x changes, and it gives us the value at x is equals to 5. If we take a value of x is equals to minus 7, then the value of y also changes, and it gives you the value of x is equals to minus 7. So essentially, as we keep toggling this value of x, it gives us the value of the line, it gives us the equation of the line at which would be a tangent to this curve. We saw the value of 4, 5, minus 3, let us also check the value of 7. So at x is equals to 7, which is here, the equation of the derivative would be represented as y is equals to 42x minus 147, right. Now lastly, let us also take a very quick look on the symbolic interpretation of integration. So an integration is defined as h of x is integration of f of x with respect to x. If we perform the integration of f of x, we get x cube, and this is highlighted by this curve here. So the negative values of x1 essentially means we are moving from the origin towards the negative x axis, which is resulting into the negative sign of the area. For the positive values of x1, we are moving from the origin towards the positive x axis. As a result, the sign of the area becomes positive. To summarize, this lecture essentially gives a quick recap on vectors and matrices, gives a quick recap of the symbolic maths, basic maths of solving and differentiation, lastly focusing on the calculus of it, which is differentiation, integration, and its interpretation in 2D, 3D. Thank you.